thanks for the lovely introduction. That was really nice. And yeah, hopefully I will get to talk to more of you after about the instrumentation. But I'm going to tell you about kind of some of the things I'm interested in cosmology and the instruments that we build with those. You can also interrupt me during the talk as well if you want to, but also happy to take questions after. So because I'm a cosmologist, I always have to show the history of the universe, so in one snapshot. So this is the history of the universe with the Big Bang there on the left-hand side. And what we do know is that the universe began in this hot, dense state. It expanded at an incredibly rapid rate in what we think of as inflation. And we're probing that with some of the instruments that I won't even have time to talk about today. Then after a while, the universe expanded and cooled. And at some point, it cooled enough that we were able to have photons streaming through the universe. And that's the cosmic microwave background. So a lot of the physics that we understand about our universe and how it evolved came from that. And that is also one of the things that I study that I don't have time to talk about. But what I'm going to talk about today is how the universe evolved from there. So once the universe started cooling, we started to form stars. And we kind of know how this happened in a relatively kind of conceptual way. So stars formed. Those stars started to emit photons that were able to actually ionize the neutral hydrogen in our universe. And then we kind of get around this period of reionization, these ionizing bubbles that soon filled the whole universe. And then we kind of have, in my mind, as a cosmologist that looks at things very far away, the universe as we know it today is like the second half of there. I'm sure many of you study things over here as well. But one of the things that I like about being a cosmologist is that we can make these large-scale measurements to probe many different periods in the history of our universe. And I've kind of put some question marks up there about the things that I'm interested in studying generally with these instruments. So inflation, how neutrinos change the structure of our universe across cosmic time, what happened during reionization, what happened in later time. So what was happening to star formation, how did dark energy affect our universe? We can study all of these with these kind of large-scale measurements. And what I'm going to talk most about today is reionization. So how we can measure and understand reionization. And as an instrument builder, I'm actually pretty excited about this because it's very hard to do. So the epoch of reionization spans sort of redshift 5 to 10 roughly. And what we think happened is shown in this kind of artist's rendition. So you can see there's like some objects and they're emitting photons, creating these bubbles. But exactly how that happened is still pretty unknown. And one of the reasons is that observationally, it's very far away. So it's hard to measure because these are very faint signals. And we're really pushing the limits in terms of like instrumentation that's able to measure those signals. Then the other thing is that some of those photons are redshifted into different bands than we would measure in, say, optical frequency. So you're looking at different technologies to make these measurements. So that's another reason that it's difficult. But what we kind of want to know is what was the duration of reionization, what objects were responsible, did it kind of happen in this patchy way or all at once? Like, how did reionization really proceed? And we have some measurements from many different kind of observables that help us understand reionization, but we're still a ways from understanding it fully. And this is one of the things that I'm interested in. And you end up getting a lot of other science along the way when you're building these instruments to study this thing particularly. So there are some common techniques for studying reionization. So the Gunn-Peterson effect, you can look at the cosmic microwave background actually to understand reionization because CMB photons scatter off electrons. You can look at early galaxies in the Hubble Ultra Deep Field, ALMA and JWST. So I mean, that's happening right now with JWST, right? We're like seeing very far away galaxies, and that's a piece of this puzzle that is helping us understand reionization. There's a big push to understand reionization using 21 centimeter intensity mapping, which is happening a lot in Canada, right? There's these experiments that are really trying to probe how the ionization fraction evolved across cosmic time by using a radio measurement of the 21 centimeter spin flip. And so I'll just kind of show you some of these things. So if you're not familiar with it, the Gunn-Peterson Trough happens because you have these high redshift quasars. If you have neutral hydrogen along the line of sight, you can actually get some of that quasar absorption. That absorbs those photons. And so you know if there's neutral hydrogen along your line of sight, so that helps you figure out whether reionization has ended or not. Unfortunately, it's very, very sensitive to like the tiniest amount of hydrogen. So you can figure out when reionization ended, but it doesn't give you like that like trace out of reionization that you might want otherwise. I won't really talk about the CMB, but one of the things that's happening right now is that we're going from these maps of the deep fields with Hubble to even better maps measuring higher redshift galaxies with JWST. And one of the ways that people often study randomization, and it might be one of the ones you're most familiar with, is you can look out there and look at these high redshift galaxies and say, we have these sources, they're emitting these many photons in this frequency range, and we have this much neutral hydrogen, so we can figure out how many, whether all the sources that we're counting up in the sky are enough to account for, ionizing that. And you kind of have to, the problem with that is that you kind of have to extrapolate to the faint sources that you're not actually seeing with these big optical and infrared telescopes. So you kind of have to do a little bit of extrapolating, and I'm proposing in our work to do kind of something complementary. So, of course, 21 centimeter lets you probe that same epoch with this spin flip line, and that's kind of actually very complementary to what we're trying to do here. So the instrument that I'm talking about today is called TIME, and it is really an instrument that takes pieces of studying early galaxies and pieces of studying large-scale structure using line intensity mapping to understand randomization in a different way. And I think it's going to be very complementary to these two last techniques that I mentioned, because it has different systematic effects and slightly different ways of making the measurement that really kind of will help understand some of this stuff better. So our technique is called line intensity mapping, and it is with this fine structure line, an ionized carbon line that you find in galaxies. And the reason it's powerful is that you're actually mapping a spectral line over a cosmological volume. So you're not going out there with your instrument and measuring individual sources on the sky and saying this galaxy has C+ in it, so does this one. You're basically measuring this integrated signal from the sources. And that means that you're integrating sources that are dim, much below your detection limit that you would have with a traditional galaxy survey. And you actually extract the information in the form of a power spectrum. So this kind of really helps us CMB people that we're always extracting the information in statistical ways in the form of a power spectrum. But basically, you're looking at these fluctuations, and you're thinking about how that statistically corresponds to the amount of emission you have from these sources. So I kind of like to think about it as doing a little kind of tomography, but we're not quite getting there. But basically, you can do these slices through redshift because you have this measurement, and then you can use your handy little computer to make a power spectrum with those slices. So it's very similar to measuring the CMB, and then you take essentially a Fourier transform to get your signal. But in this case, you have maps at different redshifts, so you don't just have one 2D slice like you do the CMB. And what you get from a power spectrum is this. So basically, what I have down here is I'm saying, what is this power spectrum that I'm measuring? And what you can see here is that this P of k, which is my power spectrum, is equal to I squared, B squared, times P, which is the matter power spectrum, plus the shot noise term, which we'll just ignore for now. But what this is actually telling you is that that power spectrum that you measure, if you go out and make this map, is proportional to the mean intensity in that line that you're measuring. So you're how much intensity am I getting from C2? That is proportional to that power spectrum bump that you measure at those large scales. So that's the measurement. And I said some things about intensity mapping. What's really good about it is that you do get all of that emission. And you don't really need high resolution for your telescope. So that's great because then you can measure this large map very quickly. And one of the things I like about it, but you could also consider this a challenge, is that we have a lot of models for these signals that we might measure, but we don't have a lot of measurements yet. So this is kind of a new field measurement-wise, which to me as a pro, as an experimentalist, I'm yeah, let's measure a new thing. And then this is just another artist rendition showing you, you get this 21 centimeter signal from randomization, but you also get other lines, so CO, C2, Lyman alpha. So you can do this line intensity mapping technique with any line. So you might be most familiar with 21 centimeter, but you can do it with other lines, and that's what we're trying to do here. And one of the reasons that we're trying to do this is that we think that perhaps that C2 emission line in galaxies might be very bright. We don't have a whole lot of measurements to tell us that for sure, but we're thinking, we have this C+ line at high redshift, and it's actually redshifted into the millimeter wavelength band. And as someone that comes from a CMB background, we have a lot of experience building millimeter wavelength instruments. So let's do some other science with that expertise. So this is just a handful of experiments that are trying to do this. So TIME is the one I'm going to talk to you about today. there's a lot of folks here involved in CCAP Prime, so there's a spectrometer for CCAP Prime that will do this line intensity mapping. And then there's a couple of other experiments unrelated to my work, but there's, the landscape is that we're kind of growing the number of experiments that are trying to make this measurement. It's a pretty new measurement. So time is actually a low resolution spectrometer. It's in the redshift range of 183 to 326 gigahertz. And you can see that ionized carbon line that you all might be familiar with at lower redshift, it's redshifted to 1.9 terahertz, or, basically you can see that when it's redshifted, it's actually in the 200 to 300 gigahertz range. So we're building a spectrometer that can measure that redshifted line. So the time collaboration is a large group of people at many different institutions that I've listed here. So a lot of this work is all of our combined work. And we also actually have a lot of undergraduate students working on the project. So this is some of my students last summer leak checking the time receiver. So that's the time receiver, and then that's some of my students taking a selfie with the experiment. And they've actually done a lot of work on time over the years. We have probably at least 20 students integrated over many years, undergrads, working on this project, as well as all the grad students, postdocs, and staff that also work on this project. So we definitely couldn't do it without all of the work of all of these people here. So now I'll kind of mention some of the challenges, and I'll kind of show you some of the ways that we're thinking about analyzing data and how we actually get a result. I'll show you some of the instrumentation, and then we'll proceed from there. So one of the things that you might be thinking immediately, what are the challenges making this measurement? Because it sounds great, right? We get all the information from all these faint sources. We get to measure a large portion of the sky so we can make a cosmological measurement. But interpretation of these measurements actually, we think, will be quite difficult. And one of the reasons is that we do get everything in our pixels. So one of the pluses is that we get everything in our pixels, but the downside is that we get foreground contamination from other lines in our pixels. And I'll show you a couple of things about how we're thinking about solving these problems. We also integrate over many small-scale properties. So tying the physics and astrophysics requires detailed modeling. And we were kind of talking about this at lunch, is that you have this complicated stuff going on, but how do you get a cosmological measurement eventually from this? That will be difficult. And this was also on my pros list. There's many models and not many measurements. So we have a lot of different, we have some range of models that says, we get somewhere from 1 to 10 signal to noise on our signal, right? So maybe this would end up being an upper limit measurement if, for example, you had way less carbon than you thought at redshift 9 or something, which I think would be actually kind of exciting. But we don't really know what we're going to see. And this is just another way. This is from one of my colleagues, just showing that there's lines emitting in the ISM. And if you're using neutral hydrogen, you're okay, we're pretty sure what we're measuring. But if you're measuring, for example, C2, it's coming from a lot of different regions. If you're using a different line, there's a lot going on that we have to understand. And this is not my field. This is modelers that join us in our teams and kind of talk about, well, once you do measure the signal, I'm this is what the density of C2 looks like over a function of Z, and then we have to figure out what that means. So this is another way of thinking about it that kind of helps put how difficult this measurement is in perspective. So this plot has just the flux in some lines versus redshift on the x-axis. And what you see is that from redshift 5 to 9, that C+ line is very bright, which is good. We're all right, that's why we want to measure that line. But what you can see is that there's going to be emission from CO lines, this whole CO ladder, at lower redshift that are actually going to be coming from different redshifts, but they're going to be in your same frequency bin. So that automatically already tells us getting all the photons in one bin is going to be a challenge. So that's what we see there. And this is kind of another way of looking at it. This is just a kind of very busy science figure. But if you look at the top panel, you can see we're just kind of thinking about, oh, you have this instrument, you're looking out into the universe, and you're getting information from C2, but you're also getting lots of signal from CO at lower redshift. And on the left-hand side, or sorry, the right-hand side, this is also just showing you kind of what line intensity mapping means a little bit conceptually, which is if you had the best galaxy survey ever, and you could go out and measure every galaxy, even extremely faint ones, you would make this measurement. But of course, you're only going to be measuring the brightest ones in any reasonable amount of time. So if you want to kind of think about it in a line intensity mapping way, you get this fuzzy, patchy, large-scale structure map, but it doesn't have what is X galaxy doing? Like, how bright is it really? But it's a trade-off. So one of our graduate students, who's now a postdoc at Northwestern, basically did some modeling to see what we would expect for a power spectrum for kind of one of the intermediate models of C2 and CO. And this was also supposed to demonstrate for a proposal that, you know, this CO removal is actually very important. So this is in the teal and purple, you have a power spectrum. So the bump on the left-hand side is just that clustering term that I was talking about when I showed the kind of theoretical version. We care about how big that clustering bump is, but as you can see that there's, you know, a power spectrum of CO potentially that is around that same level. Oh yeah, and this is Jason and my head. We're trying to calibrate something in the telescope cabin. But Jason also has a paper that we wrote as a collaboration where it has kind of all of the details for the models if you all are interested in kind of what we actually expect to measure with time. This is one of my favorite plots that Jason made. So this is the answer to how we're going to solve this problem, which is we have CO and C2 in all of our bins. Not in all of them, but you know, in a given bin you could have C plus as well as CO. So what we actually have to do, or you know, there's many different things that you could think of doing. But one of the things that you could do is that you could take an external galaxy survey, because you know that, you know, with some scatter, the luminosity in, say, an IR survey of galaxies would be correlated with like CO emission from those galaxies. There's going to be some scatter there, but they're correlated. So what we're showing this plot, even though it's quite busy, is if you just look at the green part with the yellow first, is that if you had an external galaxy survey and you masked out all of the pixels in your survey where you have bright IR galaxy luminosity, you would be getting rid of the CO as well. But if there's some scatter, you have to mask down to a certain like level in the galaxy survey luminosity to actually make sure that you're fully removing CO. So this busy plot is just showing you the teal and blue is just like saying what the C2 amplitude would be. And then as you mask different fractions, my favorite axis is like the second from the top, so F mask. If you just go down in the fraction of your survey that you're masking using an external galaxy survey, eventually you get your CO level to be subdominant to the C plus level that you're actually trying to measure. And I won't dwell too much on this, but one of the things that we have seen in, you know, more local galaxies is that the C plus luminosity is, you know, correlated with star formation rate. So if you want to kind of make your measurement instead of, you know, how much C plus do you have, but like what's the star formation rate across cosmic time at these early epochs, you could think about using a relation like that to turn then this C plus luminosity that you measure into a star formation rate. And that's interesting because, you know, you can measure the star formation rate at lower redshifts quite well, but this gives you a measurement of the star formation rate kind of further in the past, like across, it kind of broadens the cosmic time that you've actually been able to probe. And then this is another plot that's kind of like, if you all know the Maddow plot, you know, so like you can kind of think of like, you know, how does star formation rate change versus time? Well, one of the things that might help you learn about star formation is knowing how much molecular gas you have available at those like later times. So closer to redshift, like 0.5 to 2, we can actually use those CO lines that I was telling you about that we're calling like interlopers or foregrounds. We can actually use those to make a measurement. And we can see, as a function of redshift there, what the molecular gas content of the universe is across cosmic time. So the gray bins are basically other measurements. Then the blue bins are time. We've then like used some scaling to turn that into rho H2, because as you all might know, that's hard to measure. But you know, this is just saying that we can use some of our measurements to, you know, some of our measurements that we might consider a foreground and like learn something about the molecular gas content of our universe, which would be very interesting. All right, so now I'm going to kind of transition. I've kind of told you the background science, like why we're trying to do this. I'm going to tell you a little bit about how we build this instrument and like what we've been doing in our group to make this instrument a reality. So I think I already told you we need like an R of 100 millimeter wavelength spectrometer, so something from the range of 200 to 300 gigahertz. It needs to be a spectrometer. Because these signals are so faint, we need very sensitive detectors. So for our experimental design, it's basically we need something very sensitive. We're using transition-edge sensors, though you could use something like MKIDS or some other very sensitive thermometer. We need enough angular and spectral resolution to remove those foregrounds, because as you saw in that masking plot, we're going to be masking out every place there's a galaxy that we see in an external survey, if we have very big bins, we'll end up like losing a lot of our survey. And so that's why we need a large aperture telescope, and then we need it to be a spectrometer. So we're using a grating spectrometer, but on my plot that I showed, where I had like all 5 different experiments that are trying to do this measurement, they all use actually different spectrometer technology. So that's kind of something that we're a little bit excited about, and that you can maybe have instrumental systematics. Hopefully we'll be addressing those by having a bunch of different experiments in the field that are doing this with different technology. So these are the grating spectrometers. They're actually, this thing here in the center, it weighs about 25 pounds. It's 25 pounds of aluminum. So it's pretty intense. It has this curved diffraction grating that is on the macroscopic scale. So we're looking at millimeter wavelengths. So you can really see the teeth in the diffraction grating just by eye. And then we stack 16 of those up together and put a feed horn basically at this like input here. And it's basically a waveguide spectrometer, so the light goes in here, it bounces off of this diffraction grating, it's diffracted and focused along this focal arc here. So that's there. And these were designed at Caltech when I was a postdoc there, and then they were fabricated by our colleagues at AJA. And this is just a shout out to one of my high school interns actually, who took that original design and turned it into a prototype of basically 3 stacked spectrometers for them to be tested in the lab. And then once we verified this, so this is a paper about just verifying that this diffraction grating worked well as a spectrometer. This just shows 3 of the channels, how they were measured versus the predicted expectation for the signal. And once we had done that, then we made the full spectrometer, which is basically 32 banks of these giant grating spectrometers weighing like 50 pounds. And this is just like a bandpass from one of our first runs. You can see there's some channels missing, but this proved to us like, we have a spectrometer in the millimeter wavelength range. So this is just the unnormalized signal from each of the channels of our spectrometer as a function of frequency. So as I mentioned, our detectors are transition-edge sensors. So if you know these sensors, they're superconducting sensors that work at very low temperatures. So they work at 250 millikelvin. And the way they work is that you basically have a superconducting material with the transition temperature around 400 millikelvin. When you cool these sensors down, their resistance changes very steeply with temperature as they're going into the superconducting transition. And you can actually voltage bias them in that transition and kind of keep them in the steady state of like electrothermal feedback there. And they have a very steep change in resistance with respect to temperature. So when you get very small changes in power on the sky from these very faint signals, you actually see that as a very strong signal in these bolometers, and that's what we're doing there. So this is just an array of those bolometers, and if you want to see them a little bit more zoomed in, they're silicon nitride meshes plated with gold such that they have good absorption to the millimeter photons that we're looking at. They hit those gold absorbers, they warm up, and you read out that change in temperature with the transition-edge sensor that I discussed there. And of course, because we are working at these low temperatures, we actually need a cryostat. So this is a 250 millikelvin base temperature cryostat that was designed actually for a completely different purpose and then repurposed for our experiment. So if you're interested in cryogenics, there have been a couple papers written about that. But then we turned it into the receiver for the time instrument. So we take those spectrometers and detectors that I talked about, we put them in this cryostat, cool it down to 250 millikelvin, and make our measurement. So this is what the spectrometers look like in a focal plane. So this is that grating that you saw, the stack of gratings. These are the detector modules now tiled across there, and these are the feed horns, so you can kind of sort of see. There's basically 16 feed horns there, and then there's readout electronics to take those signals from the focal plane out to the world. So for the past couple years, we've been a little bit delayed because of COVID. So we had an engineering run, and then we had a pretty long delay because of COVID. We did another observation run last fall, and then we're planning to do basically 3 years of science observations starting in the fall. So these are just some pictures of the engineering and commissioning. So these are some students from Caltech and RIT at the time, plus me assembling the instrument in the lab at the Arizona Radio Observatory, which is where we deploy the instrument. This is just one of my favorite pictures because it kind of looks like when you're like in kindergarten, you have like circle time and you're like working on something together. I don't know. I really like it. We're trying to put like a Mylar sheet in front of all of like the optics, but anyways. So the students here are all postdocs now, so that's, you know. So this is now showing you the receiver cryosat, like how big it is compared to human beings. So that on the left-hand side is showing, you know, the mechanical model I showed before. And then this is us assembling it outside at Kitt Peak in Arizona. So you probably know from your experimentalist colleagues here, it's always like some rough conditions outside trying to put your instrument together. But that's us doing that kind of cold at Kitt Peak. And then this is the telescope. So this is the Arizona Radio Observatory 12 meter. It's a 12 meter dish that's used for a number of different things, including EHT, but we have time on this telescope for basically 3 years to do science observations. And this is the time Cryosat, where we're kind of getting prepared for it to be lifted, and this is it being lifted into the receiver dome so that we can then put it into the receiver cabin. So that just gives you kind of a sense of scale. This thing is like 1 ton, basically, so I don't know, it's a little scary. Right before we did this, someone told me the story about like Apex, where someone dropped their receiver off of Apex, and like I was just like, don't tell me this, like, yeah. But we've done this twice now, and the second time it was way less stressful. But this is so basically what you have to do is you have to lift the cryostat up on its side, shove it in this receiver cabin, and then this is it resting inside the receiver cabin. So the Arizona Radio Observatory 12 meter, it's a cast grain telescope, so it has its primary dish, secondary, that goes straight down into this receiver cabin, which you can kind of see a slice of here. It's a little bit easier actually to see it in the model than in my photograph. It's actually really hard to take a picture in a small cabin. But this is the cast focus. It hits this set of yellow mirrors, which is a K mirror, which rotates our field on the sky. Then it goes through the series of other coupling optics, and then there's a final mirror hidden, and then it goes up into the cryosat into some of the optics that I showed you with the detectors, feed horns, and spectrometers. And then this is it just over on the side, so this is the cryosat kind of hidden back there. This is the K mirror plus the like thing to keep people from bumping their heads. And one of the things that we did immediately during this last commissioning run is, we observed Jupiter with our instrument because it's a very bright millimeter source, and use this K mirror to track on the sky. Because one of the things that we're doing is, you might have noticed that it's a 1D array. So there's like a linear array of feed horns. It's not like a 2D array on the sky. So what we want to do with this instrument to get the most sensitivity is take our focal plane and scan it back and forth across like a 1D scan on the sky. So we get very deep observations with just one spatial direction. But as you can imagine, if you couldn't rotate your field on the sky, as the sky rotated, you would kind of like automatically get a 2D field on the sky, and that really doesn't let us get the sensitivity that we want over like a narrow piece of sky. So we have this mirror that rotates and keeps our beams in a line on the sky as we observe. So we're kind of where we are with time right now is we've done these 2 observations. We're kind of in the process of upgrading the spectrometer. So these are some students, and actually just students and me, though some of them are postdocs now, in the lab at Caltech, basically upgrading the instrument. But we're kind of in the process of upgrading cryogenically as well as detectors to get the instrument in the final state and the final sensitivity that we want it for the 3 years of observations going forward. And one of the big things that was actually very difficult is, so we did our last deployment, and it was kind of like deep in COVID, like early 2021, a year ago. And we actually had this plan where we were going to go to the telescope and do all these observations, and we were going to get remote observing working in like probably year 3 of the project. We're like, we don't need to remote observe right away. But one of the things that kind of pushed our schedule, and I think actually for the best it ended up being, though it was very stressful at the time, is that we actually ended up having to remote observe due to someone having COVID. So we actually got our remote observing software working, and this is just a screenshot of us doing remote observing. And I think we're observing the moon there, actually. So like, I think it's a pretty bright source. But the red line that you see there is actually us tracking across a source on the sky using our data acquisition software, which was built by Victoria Butler, one of the grad students on time, who's now a postdoc at Cornell. So this is just kind of our observing run. So we were doing, essentially in this last engineering run, we were observing sources on the sky, such as Jupiter, the moon. We were doing noise stairs to understand the detector properties. And then we were doing scans of quasars, also for calibration, and doing some science scans. So I mentioned that 1D scan that we're trying to do on the sky. We're typical cosmological observations are usually these big 2D fields on the sky. So we're kind of trying to understand, basically, if we do science observations in this 1D scan that gets us very deep, like how is our data analysis including, masking and then doing the Fourier transform of that field? Are we going to lose modes that we really need to understand the cosmology or not? So we're kind of doing 1D scans, tests of those. We'll run those through the data analysis pipeline in the next year and then try to figure out whether we need to modify our scan strategy. So the trade-offs would be, if you do a 2D scan, you get more modes, but you also end up not getting to go as deep on a single patch of sky, of course. So yeah, this is just kind of what we were doing. So we successfully implemented remote observing, and we're working on these 1D scans. But the other thing that we really want to do is, does anyone do millimeter wavelength astronomy? Okay, obviously the atmosphere is our biggest source of noise. So some of you will try to avoid that. But one of the things that you might know, if you know millimeter wavelength astronomy, Kitt Peak is not necessarily the best site because what we really care about is very low water vapor. So if you go to a site that's very high and dry, you remove kind of one of your biggest sources of noise. So we're trying to characterize the atmosphere at Kitt Peak. So Kitt Peak actually has kind of high variability. There are very, very good days where it's very dry, but there's some very wet days. So we're kind of trying to figure out what is the stability of the atmosphere and how easy it will be to remove it in software, such that we can do this measurement and get to the sensitivity levels that we are going for. And this is kind of a slide that shows you a little bit about this atmospheric modeling. So on the left-hand side, you have basically what we are calling the PSD, but say you take the Fourier transform of a time stream that you took on the sky. So if you have a time stream that you get from scanning your telescope back and forth across the sky or just staring, you see fluctuations that are coming from the atmosphere. And on some very small level, you have a science signal in there, but the biggest signal is your atmosphere. And what we want to understand is, can we do some post-processing that actually takes the black line, which is the original Fourier transform of the time order data, or PSD, and then if you do some sort of filtering, like maybe you subtract the large-scale modes, or you do a PCA analysis, you can get rid of some of that noise. But of course, large-scale modes are what you're trying to measure for our signal as well. So we're still kind of basically doing simulations. So one of our grad students was doing simulations of the atmosphere, accounting for the actual conditions at Kitt Peak as best we can, to figure out what algorithms we actually can use that will remove our atmospheric signal without removing too much of the science signal. So that's kind of a work in progress, and that's one of the big things that are difficult in this field, basically, is how you can do that. Some of us are also in this room also work on other telescopes that will be at drier sites. So ultimately it would be nice to go to a drier site, but we think that there are actually some really good atmosphere days at Kitt Peak, and so we're just trying to verify that as well. So this is just a busy slide showing us our pipeline. So what we're trying to do before the next science run is basically to kind of incorporate all of these pieces. So take those detector time streams, talk about how you could remove bad data, do simulations, turn those into maps, and then ultimately calibrate them, turn them into that power spectrum that you saw in those early slides. So how do you take these map slices and turn them into a power spectrum? And this is being led by my new postdoc, Victoria. Okay, so now I'll just tell you a little bit about our last observing run. So this is actually a picture of the center of our galaxy. So this is Sagittarius A star. So this is taken with time. And what you see over here is kind of a false color image of the center of our galaxy. There's some striping in there, which, that's why I put preliminary on here. But what each of these panels here on the left-hand side is a channel from the time instrument. And what you can see is that, A, we're missing some channels. That's a detector problem that we're going to fix for the science run. But B, you can see the center of our galaxy at various amplitudes through most of the frequency bands. And there's a bright one over there that's like a CO line that you can definitely see. So we're kind of proving to ourselves that, we're definitely seeing the center of our galaxy. We're definitely measuring these transitions. And I mean, if anyone wants to talk about what you could do with this scientifically, this was a calibration for us, but if anyone wants to talk about what you might do if you wanted to measure the center of our galaxy in these bands, I would be very excited to talk to anyone about that. But for us, we were verifying that our instrument was working. We did a few other observations looking at the Orion molecular cloud and other star-forming regions that we know are very bright in the millimeter wavelength range with time. So I guess in terms of what's next with this instrument is that, we're going to return to the telescope once we've made those improvements to the detectors that I mentioned. And we really want to make a measurement, a power spectrum, or, if we don't see a signal, some sort of upper limit to kind of basically confirm or deny some of those models that people have made for how much C+ you expect to see over these redshifts. And, this is kind of the Pathfinder experiment. It's like, let's just try to get a detection and see if this is, something that makes sense to pursue. And then the other things that we're thinking about, as I mentioned, the atmosphere is kind of not the best at Kip Peak. So we're going to do 3 years of science observations there, and then we have this idea of moving time to Chile because it'll improve sensitivity. And also, one of the things that I mentioned is that there's these complementary measurements. Like we're trying to make this measurement that could be complementary to 21 centimeter, but we're in the northern hemisphere, so it's hard to do that if you have 21 centimeter experiments in the southern hemisphere. So one of the things that might be nice is to be in the southern hemisphere. And in general, for C2 line intensity mapping, you can do this. So basically, one of the things that I think is going to be very difficult for us, as well as 21 centimeter experiments, is if you get a signal from this epoch, is like, do we truly believe it, right? Do we think that this is from reionization, or is it some unaccounted for systematic? And we've seen that in 21 centimeter experiments, right? Like, it's very hard to get the systematics right. And I think that we actually have very different systematics in both of these two kinds of experiments, and I think it's kind of lucky and awesome that that's the case. So if you're using a 21 centimeter radio observatory, you know that you have giant beams. So you get an even giant piece of the sky, that's great. But you also pick up our own galaxy. So you have a lot of systematics from that. You have RFI, that's hard. For our experiment, you have kind of the opposite problem. So we have very small beams. It's pretty difficult to make these instruments. So it's, I think, very difficult technologically to get a big instrument on the scale of the ones that you do for 21 centimeter. But because you have small beams, you don't have so much pickup from our galaxy. Our foregrounds are really more astrophysical, extragalactic astrophysical foregrounds. So we have very different foregrounds. So I think that in the future of this field, doing those two measurements together is going to be extremely, extremely valuable from a systematics point of view. And then hopefully, because 21 centimeter is measuring the neutral medium, and C+ is measuring some of the ionized medium, if you did a cross correlation between those measurements, you could actually kind of trace out how the scale of bubbles, ionizing bubbles, evolve over cosmic time. So there's really some science in that cross correlation as well that I think would be very exciting. We have to get very, very more sensitive with our instruments to get there because we have to have modes that we share with these large 21 centimeter experiments that are measuring huge parts of the sky. So that's kind of where I see this field going. One of the other things that you can do is if you had an extremely sensitive C2 experiment, you can actually start to do line intensity mapping that lets you look at the large scale structure of the universe. So it's kind of like a way you might think of measuring all the modes in the universe. So some galaxy surveys are trying to do this. So they're trying to measure all of the modes in some specific signal. So if you can kind of think of having a frequency map, at every frequency of every large piece of large scale structure in the sky, you start to get many modes, and you actually start to be able to constrain cosmology. So this is just a reference for you all if you want to look at this archive paper. But there's a white paper talking about if you then built a spectrometer, and this is parameterized in terms of spectrometer hours, so this is just how sensitive a spectrometer do you need to do cosmology, basically. Assuming everything else goes very well, which we're still totally working on. But you can build, more and more, just making sure. You can build more and more sensitive instruments, millimeter wavelength spectrometers, that actually allow you to do some constraints on cosmology. So not just measuring star formation across cosmic time, but measuring some of the same things you could do with a large-scale structure galaxy survey. So kind of thinking about doing BAO with H1 or galaxies. You can do that with any line, essentially, if you know enough. So yeah. And yeah, so I mentioned to some of you while talking that in addition to time, which has kind of been my main focus, there's this instrument called CCAP Prime, which is also a millimeter wavelength instrument that some of you all here work on. And it's going to be in Chile at a very excellent site. So there'll be not the same water vapor problem that we have in Arizona. It's a similar, it's a little bit smaller dish, but has some similar science goals. And we also have some of the sort of infrastructure that we've built that we think will work with CCAP Prime. And then if you all know, there's a kind of US-led experiment called CMB Stage 4, which is kind of trying to take all of the experimentalists in the world that have done CMB and kind of bring us all together and say, like, what if we built like the most comprehensive experiment so that we could get down to like, so we could get very high sensitivity measurements of the CMB and do things like constrain inflation, understand the number of effective neutrino species. And actually all of this stuff kind of plays in together. And this is why I'm kind of interested in cosmology generally and these millimeter wavelength instruments specifically, is that a lot of the expertise that we have from CMB is what led us to be able to do like millimeter wavelength spectrometers. And then we're going to take some of that we learned and kind of feed that back. So these kind of all play, I think, well together in terms of building instrumentation and techniques for taking millimeter wavelength maps, turning them into power spectra. Like all of those techniques are very much in common. So yeah, there's a lot of things like, they all have large detector counts. We have to innovate in readout technology. I know I talked to some students here that were working on like innovations in readout technology. Measuring very many detectors at these frequency ranges is difficult. We need detector testing capabilities. We're going to start having large data volumes, not by most standards, but for us it's large data volumes. And then of course, like if you're talking about making a measurement that's never been made before, both in the CMB as well as in line intensity mapping, you're going to be learning about unknown foregrounds and systematic challenges, probably some that you've thought about, but there are probably some you haven't thought about as well, or at least you haven't thought were going to be a problem. So that's kind of a big challenge that I think that, those of us that have been working on this for, decades now, we kind of have an idea of how that happens, but of course, as you get more sensitive, there may be things that you haven't thought of before. So one of the things that we need to do in my group actually is that we really want to take those giant gratings. So I mentioned the gratings right there, like the 25-pound blocks of aluminum that take the light and disperse it at the millimeter wavelength. We really want to take those and go to like a new technology. So some folks in the field are already developing on-chip spectrometers, which basically takes like a grating this size and shrinks it down to something like this size. And that's what's going to allow you to get to those sensitivities that you would need to build a giant experiment that you could cross-correlate with, for example, a 21 centimeter experiment. So we really need to develop that technology. And you need better sights for atmospheric noise. And one of the things that is really kind of true, I think, around the world is that we actually only have really a handful of sub-millimeter quality telescopes. So having dedicated telescopes built to do this science is incredibly important so that you can do like, these multi-year observing campaigns. I think I can think of like 10 maybe. But yeah, so this is really important for us to do this science going forward. And one of those is called FEAST. It's the Fred Young sub-millimeter telescope. So this is a telescope that's being built. It's led by Cornell. And there's a lot of us working on it, including some of you all here, to make this telescope work and then put different modules with new technologies from polarization sensitive instruments to these spectrometers that will allow us to do line intensity mapping, understand foregrounds of the CMB so that we can do those measurements of inflation and really go forward with like all of the science I've talked about. So this is just showing you kind of the challenge. So you need to go from this giant grating to maybe 10,000 detectors. So we have 2,000 detectors total in time. So we need to go at least to 10,000 detectors. And one of the ways that you could do that are being developed by a few folks at JPL and UChicago to kind of take that big grating, shrink it down to something that you can fill a focal plane with. And really in general, like I kind of wanted you all to take away from this like the line intensity mapping concept as well, which is that there's ways that you can survey individual galaxies, but really a lot of instruments in the field are going out and making this measurement that I'm talking about where you just measure all of the photons from all of the, in whatever lines you happen to be measuring. So this is from a white paper talking about line intensity mapping. And what it's showing you on the x-axis is redshift, and then it's showing you the scale of the survey there on the y-axis. And it just kind of puts things in context, showing you the different lines that folks are trying to measure, 21 centimeter mostly, CO, C+, and then there's a lot of experiments that are doing this line intensity mapping technique using other things like oxygen and other lines. So basically, if you have an emission line, you can do this line intensity mapping technique if you have the right detectors and kind of just look at large scale structure over cosmic time. All right, yes. So I will wrap up and just say that, I hope I've told you all that there's many scientific targets for using line intensity mapping. It's complementary to doing something with galaxy surveys like JWST and ALMA. And it really allows you to probe kind of things from the very beginning of the universe up until, you know, redshift half or even closer. Some folks are doing really local stuff with line intensity mapping as well. So I think it's an exciting technique. We're building some instruments to do this, and I hope that, yeah, I hope you all are excited about it as well. And if you have any questions, I'm happy to answer them.
All right, so thank you for that wonderful talk. We're going to open the floor to questions. For those who can stick around, also students, there is an opportunity to meet again our speaker in the lounge with. We'll go check on the Timbits,
yes,
collection of Timbits.
I'll just take them with me, so you'll want to meet with me.
But yeah, let's open the floor to questions. First of all, are there any questions coming from students? You need a few more moments. That's okay. I can see Mark had his hand up, so we'll let Mark go first.
I kind of have a two-part question, which is typically when I think of reionization, you know, redshift 6 to maybe 11, 14.
Yeah.
But using your C2 line mapping, it looks like your frequency band gets to like maybe 9.
Yeah.